Good afternoon, Namaste. This is NARSIMHULU, Associate Professor of Department of ECE, St. Peter Engineering College, Hyderabad. Today we are going to be discuss about generation and demodulation of FM. In last video, we discussed about this how the narrowband frequency modulation derivative part and wideband frequency modulation derivative part, and we have taken some comparison statement between AM and the FM. Okay, in terms of the modulation index, in terms of the complexity, in terms of the noise immunity, in terms of the standard equation. Okay, all these parameters we consider to compare this AM and FM. So now we look into this generation and demodulation of FM. Generation of FM, or you can be say it is a FM modulator. Basically, there are two types or two methods for generating FM signal. Direct method, it is a parameter variation method. Basically, you are taking the circuit is a Hartley oscillator to generate the direct FM. And indirect method, it is also called as a Neil Armstrong method. In direct method for generating FM signal, frequency modulation is done by using the voltage control oscillator. What is the meaning of voltage control oscillator? Oscillator itself, it is going to be generate the sinusoidal wave. It is having the frequency. The frequency is going to be vary according to the giving input for this VCO. Here the input is a modulating voltage. Okay, that is a modulating input. Okay, here the variation of the amplitude of this input signal is going to be impact over the what is the frequency of the VCO output signal. VCO, it is an oscillator whose frequency can be controlled by applying the external voltage. In a VCO, the oscillation frequency change linearly with the control voltage. Now you have to be make it to mark that the control voltage is a modulating voltage. Thus, in direct FM generation system, the instantaneous frequency of carrier wave is varied in accordance with the baseband signal, or you can be said the modulating signal amplitude variation by using the VCO. Then look into this one. What is this one? It is a Hartley oscillator. It consisting of the biasing network R1, R2, RE, and RC is a collector resistor. Here coupling capacitor having the transistor is configured in the CE, and L1, L2, C, which are formed like a L1, L2, C, which are formed like a tank circuit. So the output signal frequencies depends upon the L1 and L2 and C. Generally, we know that when the frequency of the output of this circuit is given like F is equal 1 by 2 pi under root of L1 plus L2 into C. But here we have to be use this Hartley oscillator for generation of FM. So we have to be make some alteration in the Hartley oscillator by adding the one extra component which is ensured with the capacitor, that is a variactor diode. Variactor diode is also called as a variable resistor. Okay, this variable resistor or variactor diode, its capacitance is depends upon the what modulating voltage or control voltage you are applying to this circuitry, so that it is going to be control the output of the signal frequency. Then instantaneous frequency of this Hartley oscillator signal, it is equal to the 1 by 2 pi under root of L1 plus L2 into C plus C dash. You can see what is the relation between the C dash and W. This W is nothing but depletion layer width. Depletion layer width. You know, we have the relation between the capacitance of the variactor diode and depletion layer width. Ct is equal epsilon A divided by omega, or W you can be say. Here epsilon is nothing but permittivity of the material, A is nothing but area of the junction, W is the depletion region width. Okay, depletion region width is going to be changed by applying the some controlled voltage over that variactor diode. Generally, that diode, the variactor diode is operates in the reversal bias. Okay, let's look at this one. In case 1, let me consider M of t is a positive voltage. When the M of t is a positive voltage, then diode is a reversal bias. Let me consider diode is a reversal bias. M of t was connected like this. Then depletion layer is increases. So you know that one, when depletion layer increases, then what happens? Capacitor is going to become decreases. You see here, you know this one. Your capacitor is going to be decreases. C dash is going to be decreased according to your circuit diagram. When C dash decreases, then you can be understand this one. then C dash decreases. This C dash was in denominator point, so instantaneous frequency increases. Instantaneous frequency increases. Then look at this case 2. M of t is equal minus voltage. It means in negative off cycle, that is. Then this diode will become forward bias. Then what happened? Depletion layer decreases. When depletion layer decreases, I just say that when it is decreases mean C of t is increases. Okay, when C of t increases, this means this C comma is increases. When this C comma increases, then it is in the denominator though. So Fi is going to be decreases. The instantaneous frequency of the Hartley oscillator is going to be decreases. It is a simple phenomena. It's look like a voltage control oscillator. So by applying the some external voltage to the Hartley oscillator, that is nothing but M of t, which is going to be control the frequency of the output of the circuitry. Generally, according to the definition of your frequency modulation, means here the frequency or instantaneous frequency of the FM modulator, okay, is going to be linearly vary with the amplitude variation of the message signal. It means the frequency you are defining in terms of the capacitors and in terms of the inductor. So one of the capacitor, which is part of the defining that what is the frequency of your signal, this is going to be changing by varying this amplitude of the modulating signal or message signal. It means there is an impact of change of frequency of the output of the oscillator. It is depends upon amplitude variation of the message signal. So you can be say this one Hartley oscillator by having the some modifications in the circuit can be converted as a voltage control oscillator. So it can be used as a frequency modulator. Then indirect method of frequency modulation or Armstrong method. In indirect method of generating wideband frequency modulation was first it produces uh, narrowband frequency modulation. Okay, then the carrier wave is baseband signal M of t. Then the resulting narrowband frequency signal is multiplied to obtain the wideband frequency signal as shown in figure. You know that one. Here we have it is a narrowband phase modulator. Already you know that when you using phase modulator, you have to be integrate the signal. We have the integrator for the baseband signal. Then it is applied to the narrowband phase modulator. Then resultant output is the narrowband FM. This thing already we discussed when you are going with the derivative part of the NBFM. And then you apply the frequency multiplier. Then you will get the wideband frequency modulation signal. Then the output of the phase modulator is a narrowband frequency modulator signal, which is denoted by the S suffix NBFM of t. Thus, for the sinusoidal modulating signal, you can be write AC cos 2 pi f1 t plus beta sin 2 pi fm t. Fn is the frequency of an oscillator and beta is the modulation index, which is kept less than 1. Okay, because it is a narrowband frequency modulation. That is very important to remind this point. And then you can be understand this is how the cos theta, AC cos theta or AC you can be considered is equal to 1. AC cos theta I of t, you can be write this one is coming to the input of the frequency multiplier. So you will get it is output is the AC cos n theta. Okay, n theta I of t. N is going to be multiplied with the angle of the cos function. So when narrowband frequency modulation is opposite to the frequency multiplier, we will get the wideband frequency modulated signal. As you say that when n is multiplier, then you can be say this wideband frequency modulated signal is AC cos 2 pi n f1 t plus n beta sin 2 pi fm t. Then you can be write this one AC cos 2 pi fct plus beta naught sin 2 pi fmt. You can be write beta naught is equal n beta, it is greater than 1. Okay, n beta is greater than what the beta was, it is very small. It means it is less than 1 according to the narrowband frequency modulated signal requirement. Once you are applying with the multiplier, so n is going to be multiplied with beta, so beta is going, new beta will come, it is greater than 1. What about the NFN? NFN mean F1 was oscillator frequency, it was very smaller, but actually for wideband frequency modulation we need to be keep this one frequency should be very high so that it is multiplied already. You will get resultant carrier frequency and is called FN. Sorry. The demodulation of FM. Here we have the two ways to demodulate FM: frequency discrimination method, that is one way. Okay, frequency discrimination method. It means and phase discrimination method. It is In frequency discrimination method, we have the slope detector, the balanced slope detector. In the phase discrimination, we have the Foster-Seeley detector and radio detector, ratio detector, and next one is the PLL detector. Generally, for FM demodulation, PLL demodulator is preferred because except PLL, all the other demodulators require a transformer for their construction. So let us go through this before going to the PLL detector. What is the basic function, how it is going to be demodulate FM signal by using slope detector and other different types. Okay, then we look at this one, the slope detector. Slope detector can be constructed with the help of the two-node amplifiers and envelope detector. Two-node amplifier and envelope detector. Here we have the two-node amplifier and we have the envelope detector. The FR is greater than F max, is nothing but FR is nothing but resonant frequency of the two-node amplifier. It is greater than F max. Okay. Then what is the maximum frequency of the FM signal? F max is nothing but maximum frequency of the FM signal. It's not meaning of maximum frequency of the modulating signal. Maximum frequency of the carrier signal after modulation. That you should be understand, it is F max is nothing but output of the modulator signals maximum frequency. Means FM signal maximum frequency. Generally, maximum frequency you can be obtained in the positive peak of your message signal. Okay. And at the negative peak of the message signal, it is a negative. Okay, negative frequency. Then a two-node amplifier. This one is a two-node amplifier and envelope detector. This is you can be say this one is an envelope detector. Okay, right? Two-node amplifier used as a frequency to voltage converter. So we can say that frequency modulated signal is converted into a amplitude modulated signal. Okay. Now we know that an AM signal can be easily demodulated with help of envelope detector. Therefore, we get message signal that was frequency modulated. Then this one is a M of t and this one is a FM of t. This is a modulated carrier. Then you are applying to the two-node amplifier. Okay, two-node amplifier is gain is like this, and this one is you will get this two-node amplifier output is the AM signal. Then you are applying to the envelope detector. Then you will get the resultant M of t. It means the process which is follows like this. You are applying FM signal to the two-node amplifier. Two-node amplifier is converting into the AM signal. Then AM signal is going to be applied to the envelope detector. Envelope detector will be take it envelope of the AM signal, that is M of t. M of t is similar to the what M of t you were used while you are doing the frequency modulation. Then F max, you know this one. F max is a 1400 kilohertz or maybe F minimum is equal to 2 kilohertz. You should understand this very simply. F max is a 1400 kilohertz mean. It means it is going to be obtained when you have this one input signal at positive peak. F minimum you can obtain at the input signal at negative peak of the modulating signal. Then FR should be F max. It means it should be greater than F max. FR is 1600 kilohertz. Okay. It means that the resonant frequency of the two-node amplifier should be greater than F max, means they decide that one 1600 kilohertz. It is feasible and it is good for to choose this one to design the two-node amplifier. Since gain frequency characteristics of two-node amplifier is a non-linear in nature, therefore some non-linearity is introduced in the frequency to voltage conversion. Therefore, message signal cannot be perfectly reconstructed and error is introduced known as the slope error. Okay, that is a problem while you are converting a frequency modulated signal to the AM modulating. There might have some problem because of the two-node amplifier is non-linearity, so it is having some errors. That error you can be called as a slope error. And let us move to the next part to overcome the problem of this slope detector. Okay, to overcome the problem of this slope detector, we'll go with the balanced slope detector. In balanced slope detector, it is designed with the help of the two slope detectors that are connected in such a way the resulting slope error will be minimum as possible. That is, the slope error is going to be become very small by using the balanced slope detector, actually, which was more in the slope detector. The upper and lower resonant circuits are tuned to frequency above and below the unmodulated carrier frequency. Okay, here we have the upper slope detector, this one, and this one is a lower slope detector, which is going to be tuned with the two different frequencies. Upper path is tuned to the higher frequencies, and lower PROF is tuned to the lower frequencies while comparing with unmodulated carrier frequency. As the Fi of t changes, the amplitude variations tend in opposite direction. By taking the difference of these variations, we can obtain that resultant frequency to voltage characteristic shown in S curve. This one is how the balanced slope detector is working. Okay, right? And another part, okay, phase lock. Already I told you know that one having many problems are there, all the remaining circuits which are used for the demodulation of FM, but only phase lock loop is good to demodulate FM signal. Let me consider. This one is a circuit diagram. We have the multiplier, low pass filter, and voltage control oscillator. Already you know that one voltage is a voltage control oscillator. We have the input signal voltage having the output signal which is having a frequency. It's going to be changed with the linearly variation in the input signal. Okay, low pass filter is going to be avoid the high frequency components, allow only low frequency components. Here multiplier is producing the components by multiplying inputs of this, that is SFM of t and SV of t. Then PLL used for the demodulation of FM signal. The input of the voltage control oscillator will be the message signal M of t, which is taken as a feedback from the output. Okay, like as a message signal, amplitude changes corresponding the frequency of VCO output will be changed so that frequency synchronization can be maintained with respect to the FM signal, which has to be demodulated. Then SFM of t is equal to AC cos 2 pi f1 of t plus 2 pi kf, okay, integral of m of t dt. Then VCO output you can be right like SV of t is equal to AV sin 2 pi f2 t plus 2 pi kV integral of V of t dt. Okay, this kV is nothing but voltage sensitivity. Here VCO output should have 90 degrees phase shift with respect to the transmitted carrier. Then for the reconstruction of M of t, we have to be follow some conditions. Okay, F1 should be made equal to F2. Then PLL is said to be in lock mode. Okay, pi 1 of t should be made equal to pi 2 when the PLL is said to be capture mode. VCO forms negative feedback for the PLL demodulator. Because of this negative feedback, within the short time F1 is made equal to the F2 and PLL is said to be lock mode. Then F1 is equal to F2 is equal to Fc. Then SFM of t is equal to AC cos 2 pi Fct plus pi 1 of t. SV of t is equal to the AV sin 2 pi Fct plus pi 2 of t. Then multiplier, which is going to be having the true input, that is SFM of t into SV of t. Then you multiply this one, then you can have the resultant thing, that is pi 1 of t minus pi 2 of t is equal to pi e of t. Okay, then you can have this one, it is a phase error. Okay, this should be minimum. Okay, while you are multiplying these two terms, that resultant equation is like this, you know, ACAV by 2 sin 4 pi Fct plus pi 1 of t plus pi 2 of t minus ACAV by 2 sin pi 1 of t minus pi 2 of t. This pi 1 of t, pi 2 of t is make you to understand having the phase error. This need to be keep very smaller so that you will get the resultant function. Then multiplication output having the two components, you know that one, it is one is AC AV by 2 sin 4 pi Fct plus pi 1 of t plus pi 2 of t. Another component is AV by 2 sin pi e of t, that is pi of t pi 1 of t minus pi 2 of t. Here the first term of the above equation verify the high frequency, so it is not allowed by the low pass filter because multiplier output is going to be passing through this low pass filter. The high frequency components are going to be rejected by the low pass filter, so this term is going to be omitted, this term is abstracted, is going to be rejected by the low pass filter. So output is only having ACAV by 2 sin pi e of t, you can be seen. And second term, since pi e of t is very small, so sin pi e of t you can be right, it is a pi e of t. So V of t is nothing but pi e of t into h of t, you can be say. What is the h of t? H of t is a transfer function of the low pass filter. Then you applying this one Fourier transform for this, V of f is equal pi e of f into h of f. Then we know that one pi of t is equal to pi 1 of t minus pi 2 of t. Pi of t is equal to pi 1 of t minus pi 2 of t. What is the pi 2 of t? Already we know that one, it is 2 pi kV integral of V of t dt. Then pi of t is equal to pi 1 of t is equal to 2 pi kV pi e of t Okay, v of t, you know that when v of t from here, you can be substitute this pi of t into h of t dt. Then differentiating both sides with respect to t, then you can have the equation like this: derivative of pi 1 of t minus 2 pi kv pi of t convolution h of t, taking Fourier transform for this one. Okay, taking Fourier transform from this one, then you will have the resultant of this one jf pi 1 of f. Then pi of f is equal to j of pi 1 of f divided by jf plus kv h of f. When h of f is increases, then pi f is going to be decreased. From the above expression, it is clear that pi f will be small if h of f is large, and if pi of t is small, then pi 1 of t is almost equal to the pi 2 of t. Okay, then h of f is not equal to the infinite, not possible. Pi of f is equal to 0, pi 1 of is equal to f pi 2 of t. Hence, by maintaining a pass band, gain of the low pass filter to be very high value, pi of t becomes very small, and pi of f is equal to jf pi 1 of f divided by jf of 1 plus kv by jf h of f. Then jf is going to be gets cancelled. The remaining 1 plus kv by jf h of f is almost equal to kv divided by jf into h of f. H of f is a very high. Then pi of is equal to pi 1 half divided by kv divided by jf into hf. From equation 4, then you can be write v of f is equal to pi of f into h of f. Then v of f you can be write like this. Then a negative feedback found by VCO is responsible for lock mode, and low pass filter LPF is responsible for capture mode. PLL demodulation is based on the differentiation method. Taking inverse Fourier transform for this one, so V of t you will get back, that is 1 by 2 pi kv derivative of pi 1 of t. 1 by 2 pi kv derivative of pi 1 of t was replaced with 2 pi kf integral of t dt. Then integration differentiation 2 pi gets cancelled, so that you will get it is v of t is equal to kf divided by kf m of t. That is v of t is proportional to the m of t. That is the kf is nothing but frequency sensitivity, k is nothing but voltage sensitivity. This is total scenario. Finally, you can be conclude that one output of this PLL is directly proportional to the m of t.